Hello and welcome back. We are going to continue mechanics of materials for part 2. The objective of the lecture is to understand the following points: the stress and strain relations for mild steel. Second point, thermal strain and how it is causing stress, shear stress and shear strain, bending moment and bending stress, and finally the torsion and angle of twist and shear stress. During performing the tensile stress for a specimen of mild steel, if a relatively small force is applied to ductile material steel and starts to deform, that means that the steel is in stress and we can measure the strain, then we will have a curve which is initially a straight line, as we can see, from the starting point until point A. That is up to point A from the origin. From A to B, the ratio is not proportional, but from B to C and together with D, the metal suddenly extends with no increase in load. If the load is removed, at that point, the metal will not spring back to its original length, but it will return to another routing, but it will not come back to the 0 point. This point B, we call it limit of proportionality, and from D to E, this extension is no longer proportional because it's taking another slope, and we will find out that there is increase in the strain. And if the load is removed little or no, it will not spring back. No spring back will occur. They are dividing the relationship into regions. First region is elastic deformation. Second is plastic deformation. And third, necking, ending with fracture. We start to discuss about the definitions. Point A is a proportional limit. The point A is the point on the stress-strain diagram to which the stress is proportional to strain. Point B is called the elastic limit. It is the point of the stress-strain diagram up to which the material remains elastic, i.e. if it is loaded, the specimen regains its original length without any permanent set. We come to C, which is called the upper yield point, while D is called the lower yield point. It is the point of the stress-strain diagram in which there is appreciable deformation without appreciable increase in the stress. There are two yield points, upper and lower points. Now we will talk about point E. E is the ultimate strength. It is the highest ordinate attained by the stress-strain diagram. As we can see, that this is the highest ordinate, the maximum stress in the curve. While final point F, rupture strength, it is a stress at which the material breaks. Stress-strain diagram will be nominal when the original cross-section area is always taken into account for calculating the stress. The rupture stress point E will be lower than the ultimate stress. We will find that this value, the ordinate, is lower than the value of E. We'll talk about what is the secant modulus. Secant modulus is the slope of a line drawn from the origin of the stress-strain diagram and is intersecting the curve. Therefore, the secant module can take different values depending on the location of intersect. Because I can take point here, then I connect to the origin, but the slope will be different. In some materials, it is hard to estimate the elastic deformation. That is why they are using the secant modulus, because they are unable to define the first linear portion, which is where E is equal to the stress over strain, and also they are taking what is called tangent modulus. They are taking tangent in this area. Here is a definition of the tangent modulus. Tangent modulus is defined as the slope of the line tangent to the stress-strain curve at point Tangent modulus is defined as the slope of the line tangent to the stress strain curve at a point of interest. This is suppose this is point A, this is a point of interest. If I take tangent here, then I will get what is called tangent modulus. Can have different values depending on the point at which it is determined. For example, the tangent modulus is equal to the Young modulus when the point of tangency falls within the linear range of the stress strain curve. If I take this point here where we have the linear portion, then this tangent modulus will coincide with the elastic deformation. The line will be coincide with each other, but outside the linear elastic region at point A, shown for example, the tangent modulus is always less. You'll find that the slope here is less than the Young's modulus. This linear portion is called Young's modulus. Tangent modulus is almost used to describe the stiffness of the material in the plastic region, and it is denoted by E tangent ET. What about the proof stress? When a yield point is not easily defined based on the shape of stress strain curve, an offset yield point is arbitrarily defined. The value for this is commonly set at 0.1 or 0.2% plastic strain. Suppose I want to get the yield point, then I will start from here, taking either 0.1 or 0.2% of plastic strain. Then I will make a line which is parallel to the E, Young's modulus, starting from 0.1 or 0.2 according to the specified requirement, and then I'll make parallel. I will intersect the curve at point C. Then the ordinate will constitute the yield and is called proof stress. So here I'm taking the parallel, intersecting the curve at point C. This is the proof stress. This is the proof stress, which is equivalent. We can call it offset yield point. Thanks a lot, and see you. We'll continue next time. Goodbye.